Hello, I am Solomon Yuko from FTC First Tech Challenge Team 1700 NewT.exe, and I will be presenting about Java programming for FTC. So the presentation will consist of an introduction, background information, and then finally subsystems explaining some various principles and details about those subsystems. And then finally I will have a Q, and then in the live talk I will have at Battle of Baltimore I will have a Q&A. So history. So NewT.exe formed from Wizards.exe in 2019, and we've gone to Chesapeake Regionals every single year, and we're part of the EXE Alliance and Rockville Robotics Incorporated. Our team members consist of see, seven seven team members and me, the software team mentor. And the programmers, so I'm the mentor, Solomon Yuko, and then we have three programmers: Daniel Anker-Scherer, who's just primarily just a programmer; Bernard Jin, who's team captain; and Abigail Zhang, who's new this year. So background information. So first, I will go over the changes made in FTC SDK version 8. Then I will go over how the FTC control and communication systems work. I will explain the different ways to program for FTC. I'll give a bit of background about Java and Android and some information about using other programming languages. So some of the changes are some stuff has been moved around or removed. There have been improvements to exception handling, so they now show stack trace, for example, which is very helpful. The robot controller inspection report has a QR code. I put a comment there about any change can break somebody's workflow. So like, some of these are pretty obviously going to break stuff. Some of them are pretty obviously good, but it's possible they still break something. Hopefully not. Okay. Let's see. So control communication systems. So the robot is connected to either a control hub or an expansion hub with a robot controller phone. The newer system is the control hub, and you can optionally add a second expansion hub. And the control and expansion hubs connect to a variety of devices, such as, so first of all, you need a battery, and then beyond that, you can have motors, servos, and I2C and various kinds of sensors. Let's see, and then that communicates over either Wi-Fi Direct if you're using the robot controller phone, or Wi-Fi if you're using the control hub, to either the driver station phone or the driver hub, which is newer, and that's connected to the gamepads, which allow the drivers to control the robot. And the robocall communication protocol version changed in SDK 8, so you have to update. You have to update both the driver and control hubs. You can't just update one of them. So, blocks. It's based on Google Blockly, and it's converted to Java. It's easier for beginners, but for advanced programmers, it can make things more difficult. See, onBot Java, it allows you to make full use of Java. Something is a bit buggy, that they've improved that lately, and there's now beta support for Java 8 for compatible devices. And then finally, there's the Android SDK, also called Android Studio. You can also use IntelliJ or possibly some other IDE, although it's not normally used. This allows you to use Java, but also other languages such as Kotlin, which I'll explain more about later. You can add external dependencies such as Roadrunner using Gradle. It gives you extremely powerful code refactoring and autocomplete. You can use version control such as Git. You do need to install it, and it's a bit slow sometimes, is the main drawback. And it uploads over USB, although it might be possible to configure Wi-Fi, whereas others always use Wi-Fi. And note that the Gradle dependencies have now been updated to to version 8 and to PowerPlay. Let's see. So Java, it's an object-oriented programming language with C-like syntax, as you can see here. It was released in 1995 by Sun Microsystems, and it's intended to be platform independent, write once run anywhere, but it's not perfect at that, because it's just really hard. It runs on the JVM, or Java Virtual Machine, and you use the Java Development Kit, or JDK, to compile it to compile the Java source code into class files and jar files, which contain multiple of them. See, Android was founded in 2003, and it's now owned by Google, and most of its and it's generally designed to be used by Java, and it uses APK files containing Delvik executables, and it runs on the Android runtime using OAT files now. Okay, so other programming languages. The main one used in FTC, other than Java, which is pretty much everyone uses, is Kotlin. It was created by JetBrains in 2011. And the main thing it does is it enforces nullability. So null basically means no value or nothing, and any non-primitive type can be null in Java, and that can cause null pointer exceptions where you don't expect them. And it also adds various syntax sugar, such as null operators, like operators for handling null in various ways. You can overload operators with operator methods. You can access you can use properties instead of getters or setters, so you can use like normal assignment syntax instead of having to call set, for example. Here, for example. You use double equals for dot equals, and triple equals for reference equality, which is double equals in Java. Basically, in Java, Java's double equals and Kotlin's triple equals check reference equality, meaning that they have to be like an identical object, not just copies. Whereas you use dot equals in Java or double equals in Kotlin to check if it's an equivalent value. Also, Kotlin provides convenient syntax sugar for automatic constructor, property, and two-string declarations. In Java, you can use annotations from Project Lombok to do this. And it's used by some FTC teams and by libraries such as Roadrunner. And then there are other possible languages that you can use, although they're not used much as far as I'm aware. You should be able to use other JVM languages, such as Scala and Jython, as well as other languages via JNI, such as C++ and Rust. JNI is Java Native Interface, and it's unclear if this is actually game legal, so consult with your rules master before you use it in competition. And note that it may or may not provide the performance benefit you expect, because JNI transitions have a lot of overhead, and the JIT compilation can result in close to native speed, or possibly even better depending on how things work out with dynamicity. Okay, so subsystems. So first, telemetry or logging, then sensors, then complex subsystems such as the intake or outtake, then vision, then Gamepad input, and then Drivetrain. So, telemetry or logging. So there are 4 different methods that we use to send different subsets of data, because they each have their own advantages and disadvantages and use cases. So, the most common one is telemetry, which goes to the driver station, and it's strongly recommended to keep it to a single screen and so that drivers can easily just look down at it and see what they need to see without having to mess with scrolling. Um, let's see. Android Logcat is also built in, and you can access it via USB or Wi-Fi, and it saves a file, unlike Telemetry, but it gets deleted after a few runs, I think, and includes information from other Android systems in there too, rather than just what you tell it to output. Let's see. Another option is the FTC dashboard, which is separate but related to, but works with Roadrunner, and it can with Roadrunner it can show the robot position and path, and I guess that's really part of Roadrunner that uses dashboard to show that, and they can also create graphs from data you give it. So, like, for example, if you want to like plot the position or velocity or power of a motor or something like that, you can, or sensor data, you can do that, and you can show multiple graphs together. And that you can access over Wi-Fi, and it's not saved. And then the last thing we did was create a custom log file. We used deflate compressed JSON, but you can really use whatever works for you. Let's see. So for the file name, what we did was we had included the build time to make sure we had a reliable source of time because the control hub sometimes resets its clock for some reason. The git commit hash and modification status to keep track of what version of the code we're running. The startup time from calendar allows you to determine when you started it, again assuming that the clock didn't reset. And then the now time helps make sure the file name is unique, so you don't like overwrite old log files by accident. Let's see, sensors. So one thing to note is that sensors return default values, which are usually 0, but for distance sensors, because of the math they apply to the data, it's not 0, but some other fixed value, depending on the mode. And there's some things you can do to check it, but it's complicated and slow. So make sure it actually is a big deal before you try to check it. And let's see, some changes are, so the most important one is that devices are now initialized when you get them from the hardware map, rather than initializing everything at the start. So if you want to initialize everything at the start, you can use hardware map.iterator, which will automatically initialize all devices, or if you need iterator but without that, you can use unsafe iterable. So basically the key thing you do is if the first time you retrieve a device is in run, your robot's probably gonna be unresponsive for a couple of seconds while initialize the device. So make sure to initialize them in init. And you probably want to either create a variable or a field for them and store them there. Let's see, there's some other minor changes. One breaking change is that the axis rotation rates for the IMU were accidentally put out of order, and now that's fixed. So if you double check that your IMU code for rotation still works, and you might need to swap some axes and signs if needed. Let's see. So complex subsystems. So we have an example with our robot with the intake and outtake. So here it takes in the ball, transfers it, uses various sensors in the process, and then it dumps it out the back. And it has a lot of moving parts and sensors involved and various states. So it uses this enum state here to keep track, as well as various other fields. And having this enum for state, make sure that you always cover all the states and don't miss any. And also, if you have a complex subsystem, if possible, create an interface around it. It doesn't have to be a separate interface, just like a set of methods on a class, that you communicate with it rather than directly messing with it with the internals, so you can easily change them without having to change all your code. Um, there's a new example added to the SDK in concept external hardware class, which uses robot hardware. And also, when you're creating these complex subsystems, one thing you need to make sure of is that you can't get into a bad position or transition badly, because that could break the hardware. So be nice to the hardware team, and they'll be nice to you, hopefully. Let's see. Yeah, also if you have separate components such as motors, for example, that have shared behavior, you might want to create a separate class for them to encapsulate that behavior. So you don't have to repeat it or change it everywhere as needed. And this is our another example of the states from a couple years ago. Let's see. I've already seen it. This is depositing backwards, and then we can also rotate this side, so it's a lot of different states. Okay. For vision, so there's they've updated the concept Vuforia for this season's images, and it works well for those rectangular images they provide, but it's not really useful for much else as far as I'm aware. And also, it takes some time to detect, like a few seconds, and its accuracy is not great, so just keep that in mind. TensorFlow is officially encouraged, and they've updated the model and parameters used in concept TensorFlow object detection, so you can take a look at that if you want to forget how to use it best. But in the past, we weren't able to make it work reliably, and first we tried implementing it manually by getting the image data and processing it in Java, but that encountered some bugs we weren't able to fix. So instead we decided to use Easy OpenCV, and the HSV hue, which is the color like red, yellow, green, cyan, blue, magenta, ignoring like black or white. So that worked reliably in different lighting, which is important because we don't know what the lighting of the competition is going to be like, and it could even be variable, and like could be different from what we have at home. So hue should work well for that. And also, there's occasionally glitches in the input image, so it's might be a good idea to take multiple samples and figure out, like, average them out or figure out which one is the most common and use that. Let's see, Gamepad input. So for buttons, you might want to create a button interface so you can have different kinds of buttons. For example, you might want to have it activate. The default is to activate while it's pressed and not while it's not pressed. But you might want, for example, have it activate when you start pressing it once and then stop activating, so you can perform a single action rather than going into state and like continuously doing something. And you can also combine that with a toggle, so you can like press it once to turn one way and then press it again to turn the other way. And so you can create a composite of action button and toggle button to make that work. And yeah, you would have a pretty simple interface, updating with a new value, and then you might want to have a way to just override it, because that could be useful. Let's see. For the drivetrain, for autonomous, Roadrunner worked well for us because it allows us to easily create complex paths and movements and take advantage of error correction and, once allowed, odometry and so on. Let's see. You might want to create a drivetrain class to keep track of the motors and the pattern of what power needs to go which way to make it move in a particular direction. And so some methods we have are setting the power in each direction, setting the power for each motor for other modes, setting or incrementing the target position, um, waiting until the target position is reached in all motors at once, either that or reached in each one at least once, and then you can also add a margin to that. So that way, like, if it's close enough, you're not spending there waiting for exactly to line up before moving on to the next step. But you probably don't need that if you're using Roadrunner. Let's see, setting the mode to all of the motors and likewise zero power behavior. Resetting the target positions. Also waiting until each of the motors is either was done moving at least once or is done moving. Also, yeah, these work with run to target position. And you can also just see if any of the motors are moving. So those are things, some of the methods you might want to include. And then in live talk, we'd have a Q&A here, and here are some links to our, first of all, these slides, if you can go back and take a look at them more carefully. Our team's website, our YouTube channel, which this will be posted on, an interest form if you want to if you want to apply to join our team, our team's email address, and my email address. I don't check the team email address, so if you want to ask me any questions or send me any feedback or anything, please send to my email address as well. And then finally, here are the image credits for the images we used. Thank you.